Welcome to the lecture series on CFD, Part 1. This is Lecture 12 on application examples for solving linear algebraic equation systems. In this lecture, we shall analyze the performance of various solvers when applied to 4 test cases representative of equations encountered in CFD. The first test case deals with solution of a Laplace equation in 2 dimensions. For this test case, an analytical solution exists so that we can determine iteration errors at each iteration. The same problem is then studied in 3 dimensions in the second test case. The third test case is devoted to solving Poisson equation in 2 dimensions. Pressure or pressure correction equations, which play an important role in algorithms for solving the Navier-Stokes equations for incompressible fluids, are of Poisson-type. Finally, test case 4 deals with equation systems resulting from discretization of a transport equation for a generic scalar variable. The test case studied in lectures 6 and 9 is used because the velocity field is available in analytic form, u equal x and v equal minus y. The flux-making velocity is thus constant over each control volume phase. 8 solvers are tested, not all in each test case. Gauss-Seidel solver, labeled GS, alternating line Gauss-Seidel solver, that is, line-by-line application of the direct solver for 3 diagonal matrices, TDMA, along one grid line, labeled LBL. ILU solver by Stone, labeled SIP. Incomplete Cholesky precondition conjugate gradient solver, labeled ICCG. CG stub solver. Multigrid acceleration with Gauss-Seidel solver as mover, labeled MGGS. Multigrid acceleration applied to ELU solver by Stone, labeled MGSIP. And multigrid acceleration applied to ICCG, labeled MGICCG. Iterations are stopped when the sum of absolute values of residuals from all control volumes drops 6 orders of magnitude. In some test cases, the reduction of iteration errors is also monitored to show their relation to the variation of residuals. The first test case is about solving Laplace equation on a 2-dimensional square domain of 1 by 1 meter. The integral form of the Laplace equation is discretized by a finite volume method using second-order central differences to approximate the gradient of phi. The function phi equal x times y satisfies the Laplace equation, so the exact solution is obtained when at all boundaries Dirichlet conditions with specified values of the function are used. The figure on the left shows a uniform 80 by 80 control volumes grid, while the figure on the right shows isolines of phi. 0 values are specified as the initial solution estimate. Because at constant x, phi varies linearly in y direction, and at constant y, phi varies linearly in x direction, on Cartesian grids central differences are exact. Knowing the exact analytical solution makes it possible to evaluate iteration errors at each iteration. Computations are performed on systematically refined grids, starting with 10 by 10 control volumes and doubling the number of cells in each direction with each refinement. The finest grid had 640 by 640 control volumes. The plot on the left shows the variation of residual norm, the sum of absolute values of residuals at all control volumes, with iterations for grids from 10 by 10 to 320 by 320 control volumes when Gauss-Seidel solver is used to solve the linear equation system resulting from discretization. The plot on the right shows the variation of iteration error norm with iterations for the same solver and grids. Iteration errors were determined by subtracting at each control volume the intermediate solution from the exact analytical solution. We see that the residuals fall rapidly initially, but after a transition range, the line becomes straight in this log linear representation. The convergence of iterations becomes slower as the grid is refined, approximately 4 times slower when the grid spacing is halved. Iteration errors do not follow residual reduction in the early stage, but the rate of error reduction becomes eventually similar to the rate of residual reduction. The lines have a similar slope. Reduction of residual norm by 6 orders of magnitude leads to a reduction of iteration error norm
by circa 5 orders of magnitude.
This slide shows the same information as the previous slide for the line Gauss-Seidel LBL solver. The plots are similar. The only difference is that LBL solver needs circa 4 times less iterations to reduce the residual norm by 6 orders of magnitude than the point Gauss-Seidel solver. However, both solvers need too many iterations on fine grids and are thus not suitable for practical applications. This slide shows the same information as the previous slide, but for the ILU solver after stone, SIP. The plots are similar, but SIP solver needs about 5 times less iterations to reduce the residual norm by 6 orders of magnitude than the LBL solver. On the coarsest grid, iteration error is reduced by the same amount as the residual norm, but as the grid is refined, iteration error norm stays behind. On the grid with 320 by 320 control volumes, the iteration error norm is reduced only 4 orders of magnitude when the residual norm is reduced 6 orders of magnitude. Initially, the residual norms fall rapidly 2 orders of magnitude, which is not accompanied by a reduction of iteration errors. Thereafter, the lines become parallel and both norms reduce at the same rate. This slide shows the same information as the previous slide, but for the ICCG solver. The variation of residual and error norm is totally different to what was seen with the previous three solvers. First, ICCG needs much less iterations to reduce the residual norm 6 orders of magnitude than SIP solver, about 20 times less on the 320 by 320 control volumes grid. Secondly, the number of required iterations only doubles as the grid spacing is halved, while with the previous three solvers, the number of iterations was increasing by a factor of 4 with each refinement. Finally, the iteration error norm is also reduced 6 orders of magnitude on each grid, the same reduction as for the residual norm. The plot on the left shows the variation of residual norm with iterations when multigrid method is used with Gauss-Seidel solver as the smoother. The plot on the right shows the same information when SIP solver is used. In the plot on the left, we can recognize 2 iterations on the finest grid level within each V cycle, one before and one after V cycle ends. Each V cycle results in a reduction of residual norm by about 1 order of magnitude. The convergence is fastest with SIP solver. On the 2 finest grids, it needs only 10 iterations on the finest level to reduce the residual norm by 6 orders of magnitude. Contrary to single grid solutions with any solver, the number of required iterations to reach the convergence criterion does not increase when the grid is refined. It stays constant once the grid becomes fine enough. This is optimal convergence behavior. This plot shows the variation of residual norm with iterations when multigrid method is used with ICCG solver as the smoother. The convergence is slightly slower than with SIP solver. On the 2 finest grids, 18 iterations on the finest level are needed to reduce the residual norm by 6 orders of magnitude. Iterations on the finest grid level are actually not converging. Residuals are increasing. However, within V cycle, residuals drop about 1 order of magnitude. Without multigrid acceleration, ICCG is the fastest solver for Laplace and Poisson equations, but multigrid is faster with either Gauss-Seidel or SIP solver. The first table in this slide shows the number of iterations required to reduce the residual norm by 6 orders of magnitude for each grid and solver. We see that the number of iterations required to meet the convergence criterion increases by about a factor of 4 with each grid refinement by having the grid spacing in each direction for Gauss-Seidel, LBL, and SIP solvers. For ICCG, the number of iterations roughly doubles with each grid refinement. In the case of a multigrid method, once more than 3 coarser grid levels in the V cycle are available, the number of required iterations remains constant. It is fascinating to see that the Gauss-Seidel solver on its own needs over 95,000 iterations to meet the convergence criterion on the grid with 320 by 320 control volumes, while within multigrid procedure, the same solver needs only 18 iterations. This represents a speedup of 5,000. The second table shows the computing times required on the same computer to obtain converged solution on the two finest grids with various solvers. On the grid with 320 by 320 control volumes, ICCG consumes 11.4 times less computing time than SIP, although it needs 19.6 times less iterations. The discrepancy is significant because one ICCG iteration involves more computing operations than one SIP iteration. Multigrid method with Gauss-Seidel and SIP solvers consume almost the same computing time, although with SIP much less iterations are needed, 10 instead of 18. The reason is that Gauss-Seidel iterations are cheap. The second test case is a three-dimensional version of the first one. The integral form of the Laplace equation is discretized by a finite volume method using second-order central differences to approximate the gradient of phi. The function phi equal x times y times z satisfies the Laplace equation, so the exact solution is obtained when at all boundaries Dirichlet conditions with specified values of the function are used. The figure on the left shows a cross-section through a uniform 80 by 80 by 80 control volumes grid, while the figure on the right shows isolines of phi in one section plane. Zero values are specified as the initial solution estimate. Computations are performed on systematically refined grids, starting with 10 by 10 by 10 control volumes and doubling the number of cells in each direction with each refinement. The finest grid had 160 by 160 by 160 control volumes, over 4 millions in total. 3 solvers were tested: ILU solver after Stone, SIP, ICCG, and CG stub. This slide shows the comparison of SIP solver performance when solving the Laplace equation in 3 dimensions, left figure, and in 2 dimensions, right figure. We see that in 3D case, almost twice as many iterations are required to reduce the residual norm 6 orders of magnitude than in 2D case. This slide shows the same information as the previous one, only for the ICCG solver. We see that in 3D case, only about 30% more iterations are required to reduce the residual norm 6 orders of magnitude than in 2D case. This is much more favorable than the increase seen with the SIP solver. The plot on the left shows the residual histories on all grids for CG stub solver. It needs less iterations to reduce the residual norm 6 orders of magnitude than ICCG solver, but oscillations for the 2 finest grids are more pronounced. The upper table shows the number of iterations required to reach the convergence criterion on each grid. We see that in the case of SIP solver, the number of iterations increases by a factor of approximately 4 with each grid refinement, while for ICCG solver, the number of iterations doubles. For CG stub, the increase is even more moderate, from 61 on 80 by 80 by 80 grid to 107 on 160 by 160 by 160 grid. The lower table shows computing times on the finest grid. The fastest solver is ICCG, even though CG stub needs much less iterations, 107 versus 160. The reason is that CG stub solver, because it can handle both symmetric and asymmetric matrices, requires many more computing operations per iteration than ICCG solver, which works only for symmetric matrices. SIP solver works for any matrix form, but only on structured grids, while ICCG and CG stub solvers can be used on unstructured grids as well. The third test case is about solving the Poisson equation on a 2-dimensional square domain of 1 by 1 meter. The integral form of the Poisson equation is discretized by a finite volume method using second-order central differences to approximate the gradient of phi. Dirichlet boundary conditions with specified zero values on all boundaries are used. The source term in the Poisson equation is a product of 2 sine functions, as shown here. The figure on the left shows a uniform 80 by 80 control volumes grid, while the figure on the right shows isolines of phi. Zero values are specified as the initial solution estimate. Computations are performed on systematically refined grids, starting with 10 by 10 control volumes and doubling the number of cells in each direction with each refinement. The finest grid had 640 by 640 control volumes. This slide shows the performance of point Gauss-Seidel on the left and line Gauss-Seidel LBL solver on the right. GS solver needs about 4 times more iterations than LBL solver to reach the convergence criterion. The convergence is smooth in both cases, and the number of iterations required to reduce the residual norm 6 orders of magnitude increases by approximately a factor of 4 when the number of cells is doubled in each direction. This slide shows the performance of SIP and ICCG solvers. ICCG solver needs much less iterations to reach the convergence criterion than the SIP solver. The convergence is smooth in the case of SIP solver, but interestingly, the slope of the line changes at some stage and the convergence becomes slower. This behavior was not present in the case of Laplace equation. The convergence is not smooth at all times in the case of ICCG solver. On fine grids, residuals fall initially quickly and smoothly, followed by a longer period of relatively slow convergence with some oscillations. After that, the rate of residual reduction becomes fast again. This plot shows the performance of CG stub solver. It requires less iterations than any other solver to reach the specified residual level. However, because it involves more computing operations per iteration, it is not the fastest solver. As the grids become finer, the residual variation becomes more and more rough. Computing times on the 2 finest grids are compared in slide 24 for all solvers. This slide shows the performance of multigrid method with Gauss-Seidel solver on the left and SIP solver on the right. Multigrid method is ideally suited for solving the Poisson equation. On the 4 finest grids, the number of iterations required to reduce the residual norm 6 orders of magnitude remain constant with both solvers. With SIP, residual level is reduced 2 orders of magnitude within 1 V cycle, and with GS solver, more than 1 order of magnitude. This slide shows the performance of multigrid method with ICCG solver. In terms of number of iterations required to reduce the residual norm 6 orders of magnitude, this version falls between the versions with GS and SIP solvers. As was in the case with Laplace equation, the variation of residuals is not always smooth. Sometimes on the finest grid level they increase from one iteration to the next. However, multigrid approach still accelerates the convergence. For the Poisson equation with selected source term and boundary conditions, there is no analytical solution. To check how iteration errors reduce with iterations, one must first obtain a very accurate solution, for example by reducing residual level by 10 orders of magnitude or more, save it, and then repeat the calculation so that at each iteration the intermediate solution can be subtracted from the exact solution. This was done on the grid with 160 by 160 control volumes for SIP and ICCG solvers. Figure on the left shows the variation of residuals, while the plot on the right shows the history of iteration errors. In the case of SIP solver, the lines for residual and for iteration error look similar. Both exhibit a change in the slope, although not at the same time. The iteration error norm changes the slope first, somewhere around 250 iterations after the start, while for the residual norm, this happens after about 300 iterations. For the ICCG solver, the variation of iteration errors does not follow the variation of residuals. While for the Laplace equation, the error norm reduction by 6 orders of magnitude resulted in the reduction of iteration errors by the same amount, now the reduction in error is significantly smaller than the reduction of residuals. The first table in this slide shows the number of iterations required to reduce the residual norm by 6 orders of magnitude for each grid and solver used. We see that for point Gauss-Seidel solver, the number of iterations required to meet the convergence criterion increases by almost a factor of 4 with each grid refinement by having the spacing in each direction, and by approximately a factor of 3 for LBL and SIP solvers. For ICCG, The number of iterations roughly doubles with each grid refinement. For CG stub solver, the ratio is about 1.84. In the case of multigrid method, from 80 by 80 grid onward, the number of required iterations remains constant. The second table shows the computing times required on the same computer to obtain converged solution on the two finest grids with various solvers. On the grid with 640 by 640 control volumes, ICCG consumes almost 21 times less computing time than SIP solver, although it needs almost 37 times less iterations. The discrepancy is because one ICCG iteration involves more computing operations than one SIP iteration. Multigrid method with Gauss-Seidel and SIP solvers consume almost the same computing time, although SIP solver needs much less iterations, 9 instead of 80. The reason is that Gauss-Seidel iterations are much cheaper. The fourth test case deals with solving the transport equation for a generic scalar variable in a stagnation point flow field on a two-dimensional square domain of 1 by 1 meter. The same test case was used in lectures 6 with finite difference discretization and 9 with finite volume discretization. The figure on the left shows a uniform 80 by 80 control volumes grid, while figure on the right shows isolines of phi and the applied boundary conditions. Zero values are specified as the initial solution estimate. Computations are performed on systematically refined uniform and non-uniform grids, starting with 10 by 10 control volumes and doubling the number of cells in each direction with each refinement. The finest grid had 640 by 640 control volumes. When central difference approximations are used for both convection and diffusion, deferred correction or under relaxation is required because otherwise some solvers will not converge. To avoid such problems, tests were first conducted on all grids using first-order Apfel scheme for convection and central differences for diffusion. Central differences for both convection and diffusion are tested on the finest grid only. In this case, ICCG solver cannot be used because the matrix is non-symmetric. CG stub solver is used instead. This slide shows the performance of point Gauss-Seidel, GS, and line Gauss-Seidel, LBL solvers when the grids are uniform. GS solver needs about 4 times as many iterations to reach the convergence criterion as the LBL solver. This corresponds to the ratio observed in the previous test cases. The convergence is smooth in both cases, and the number of iterations required to reduce the residual norm 6 orders of magnitude increases by about a factor of 4 when the number of cells is doubled in each direction. However, the shape of curves representing residual norm history is different than in the previous cases. Rapid initial reduction of residuals is followed by a plateau with a very slow reduction, and after a while faster convergence rate starts, resulting in a straight line in the log linear representation. The convergence of both solvers is significantly faster when convection is present than in diffusion-dominated problems. On the same grid, less than 1/10 of iterations required to solve the Laplace equation is needed. This slide shows the same information as the previous one, but for the SIP and CG stub solvers. SIP solver behaves similar to the Gauss-Seidel solvers, but it is significantly faster. It needs about 4 times less iterations than LBL solver. In the case of CG stub solver, the plateau in residuals becomes a period of an increase in residuals by almost 2 orders of magnitude before rapid convergence begins. It needs less iterations than SIP solver on coarse grids and on finest grid, while at medium grid resolution, the numbers of iterations are similar. This slide shows the performance of point Gauss-Seidel, GS, and line Gauss-Seidel, LBL solvers when the grids are non-uniform, fine and near west boundary, expanding toward east boundary. The performance of GS solver worsens when cell aspect ratio increases. While in pure diffusion problems it needed about 4 times as many iterations to reach the convergence criterion as the LBL solver, now the ratio increased to above 15. Compared to uniform grids, About 6 times more iterations are needed to reach the same convergence criterion. LBL solver also needs more iterations on non-uniform grids, but the increase is more moderate, about 50%. This slide shows the same information as the previous one, but for the SIP and CG stub solvers. Both solvers behave similarly as on uniform grids, but require about twice as many iterations to reach the convergence criterion. The first table in this slide shows the number of iterations required to reduce the residual norm by 6 orders of magnitude for each grid and the solver used when the grids are uniform. We see that the number of required iterations to meet the convergence criterion increases with each grid refinement by a factor of about 3.7 for the GS and LBL solvers, 3.1 for SIP solver, and 2.3 for CG stub solver. The second table shows the computing times required on the same computer to obtain converged solution on the finest grid with the 4 solvers. Although CG stub solver needs much less iteration than SIP solver, 255 versus 422, SIP solver is computationally more efficient. CG stub solver needs 2.76 times more computing time. GS solver needs 20 times more computing time than SIP solver, while LBL solver needs about 13 times more computing time. This slide shows the same information as the previous one, only for non-uniform grids. The expansion factor in x direction is 1.44 on the coarsest grid, and on each finer grid it is square root of the expansion factor on the next coarser grid. This ensures that every other grid line on the fine grid corresponds to a grid line on the next coarser grid. That is, 4 control volumes of the fine grid make 1 control volume of the coarser grid. Because the grid is uniform in y direction, cells near west boundary have a high aspect ratio. All solvers need more iterations to reach the convergence criterion when the grid is non-uniform than when it is uniform, as described in slides 28 and 29. Because LBL solver needed under relaxation to converge when central differences, that is linear interpolation, we use to compute convection fluxes, we compare here the performance with an under relaxation factor of 0.9 and without under relaxation. With activated under relaxation, the main diagonal element of the matrix is divided by the under relaxation factor before static iterations, and the right-hand side needs to be updated after each iteration, as explained in slide 6 of lecture 11. As expected, under relaxation slows down the convergence, because we are not allowing the solution to change as much as the equations require. The number of required iterations has increased by a factor 3.7, and the computing time has increased by a factor 3.9 because of the additional update of the right-hand side. SIP is again the fastest solver, followed by CG stub. This slide shows the number of iterations and computing times required by GS, LBL, and SIP solvers to reach the convergence criterion on uniform and non-uniform grids when convection fluxes are computed using linear interpolation to determine the convected variable value at the cell phase centroid. In the case of uniform grids, all solvers need slightly less iterations to converge than when upwind scheme is used for convection. The numerical diffusion resulting from first-order discretization makes the equation more diffusion-dominated, which leads to slower convergence. When convection is present, information propagates faster in flow direction. In the case of non-uniform grids, GS needs almost 7 times more iterations to converge. The increase is more moderate for SIP solver. It needs twice as many iterations. LBL solver diverges on non-uniform grids. Under relaxation by a factor of 0.9 helps. A converged solution is obtained after 10,530 iterations. Increasing the under relaxation factor to 0.95 reduces the number of iterations to 6,602. However, divergence occurs if we increase under relaxation factor further to 0.98. Here is a summary of this lecture. Both point and line Gauss-Seidel solvers on their own are not suitable for use in CFD. The convergence is too slow and computing times are too long. ILU solver by Stone, called SIP, is much faster than Gauss-Seidel type solvers. It is the fastest solver when convection dominates, but for Laplace and Poisson-type equations, it is significantly slower than conjugate gradient-type solvers. It is applicable only to structured grids. Incomplete Cholesky preconditioned conjugate gradient solver, ICCG, is by far the fastest of all solvers tested for Laplace and Poisson-type equations with a symmetric matrix. It can be applied to both structured and unstructured grids. CG stub solver can be applied to both symmetric and non-symmetric matrices, and its performance is similar to that of ICCG. Multigrid methods accelerate all solvers. The lowest number of iterations among multigrid versions results with SIP solver, but computing times are similar when Gauss-Seidel solver is used. Depending on grid fineness and convergence criterion, the computing times with multigrid methods are 10 to 100 times shorter than with the best standalone solver.